Hi everyone. So at our last class, we started the notes for section 2.6, day 2, on related rates by doing the first two examples in this video. So if you need a little refresher because it's been a while since you've taken a look at this stuff, then please watch the video the whole way through. But if you feel like you kind of sort of get it, you can fast forward until you get to problem number 3, and please, take notes as you watch problems 3 and 4, and then get started on your assignment from the textbook. Okay, in our first problem, it says the area of a rectangle remains 24 square feet, so it's constant, but the dimensions are changing. The length is shrinking by half a foot per second, and we have to find the rate at which the width is growing when the rectangle is 4 feet long. So a couple things. It always helps to draw a picture. So we have a picture of a simple rectangle. Its area is equal to length times width. So we wrote the formula down for you. And then we're going to say also what's given in the problem is that the area is actually equal to 24 square feet. And it stays constant. So that's important. That gives us dA dt, or the change in the area with respect to the change in time, is equal to 0. So keep this in mind, okay? There's no change in the area. It stays constant at 24 feet. So the other thing they tell us is that the length is shrinking by half a foot per second. So dL dt, the change in the length of the rectangle, is equal to negative 1/2 a foot per second. Sorry about my writing here, but I'll try to make it a little bit neater. Okay, so finally, it makes sense to write down what you're trying to find. It says find the rate at which the width is growing when the rectangle is 4 feet long. So our charge is to find dL dt, dW dt, let me fix that. Find the change in the width with respect to the change in time when the length is equal to 4 feet. Okay, so lots of stuff already, okay, and we have to figure out what we have to do with it. So if we just scoot this up a little bit, it'll give us some more room to work here. So we're going to start with our area formula. Area equals length times width. And we're going to take the derivative of each variable with respect to time. So derivative with respect to time. On the left-hand side, that's going to give us dA dt. On the right-hand side, we're going to have to take the derivative of L times W using the product rule. Okay, so when we take the derivative of the length, that's going to give us dL dt, but we'll keep the W. Okay, to that we're going to add. Now we're going to keep the length the same. We're not taking the derivative of that part of this function now, but now we have to take the derivative of the width. So we'd have dW dt. And because the derivative of w would just be 1, but because we're taking the derivative of w with respect to time, that's why we have to put dw dt in there. Same with dl dt. Okay, so now we're going to plug in everything we know. Go back up to the top, and we know that dA dt is equal to 0, right? The change in the area is 0. And now we have the width, which we have to figure that out. When the length is equal to 4 feet, the width has to be equal to 6 feet, because 6 times 4 is 24. So that's something that we had to solve for separately. So let's put 6 in there for the W, for the width. Now dL dt, hey, we know that it's minus 1/2 of a foot per second. So you're going to put 6 times that negative 1/2 plus, well, the length is equal to 4, and then dW dt. You see how, that's a good sign. We have everything replaced except for dW dt, which is what we have to find. We knew that in the beginning. So let's solve for that. So you have 0 is equal to negative 3 plus 4 dW dt. And just finish it off. If we solve for dW dt, we would have had to have added the 3 to the other side and then divided by 4. So dW dt is equal to 3/4, and that means that it's going to be in feet per second. So as the length is changing, at negative 1/2 of a foot per second, so it's getting 1/2 a foot shorter every second. The width is getting 3/4 of a foot longer per second. All right, on to number 2. So if you recall, I talked about these problems falling into like different categories. So in the second one, I refer to as a boat problem. We've got a dock, and we have a boat that is out here in the water. Here's the water. It's a very bad picture, I know. And we have information that says that this boat is being pulled in by the means of a winch. A winch is like a wheel with the handle, and there's a rope attached to the winch and to the boat. And so the winch turns around and winds that rope up. As the rope is wound up into the winch, the boat is being pulled closer to the dock. Okay? So we are going to be working with the right triangle in this scenario. Okay, so we're going to let this distance between the dock and the boat be x, and this distance, the winch above the dock, is just going to be 9 feet. That's going to stay constant because the winch is like put in place on the dock. It's not going to move. And then this is our rope right here between the boat and the dock. And that rope we're going to let be represented by just the letter r in our problem. So in the Pythagorean theorem, we could set this up as x squared plus 9 squared is equal to r squared, because the rope forms the hypotenuse of that triangle. Okay, in the problem, again, it says a boat is being pulled towards a dock by the means of a winch 9 feet above the deck of the boat. The rope connecting the boat to the winch is being retracted at a rate of 1.5 feet per second. That means that rope is being pulled in, and so dr dt, the change in the length of the rope with respect to time, is negative 1.5 feet per second. Okay, so they're winding it up, it's getting shorter by 1.5 feet per second. At the time that we want to look at the change in the rate of the boat, we want to see how fast the boat is going at a certain period of time. We want to look at that rate for the boat when x is equal to 8 feet. We're curious about how fast the boat is going when it's 8 feet from the dock. Okay. So we're asked to basically find dx dt when x is equal to 8. That's supposed to be an arrow there. Okay, so this is our formula right here that we are going to take the derivative of with respect to time. So we're going to do d dt of x squared plus 9 squared equal to r squared. So that's going to give us 2x dx dt plus 0, because the derivative of any constant is equal to 0, and that's equal to 2r dr dt. Okay, let's plug in what we know. We have 2, and then we have x. Well, x is equal to 8. Then we have dx dt, and that's equal to 2 times r. Okay, so we're going to have to solve for r in a second. I'm going to leave that blank. And then we have dr dt. Well, we do happen to know what dr dt is. That was given to us. It's negative 1.5 feet per second. Okay, back to finding r. So recall that this is a Pythagorean theorem equation, and we know that x is equal to 8 at this particular moment in time, and the winch is 9 feet above the deck of the boat. So we have 8 squared plus 9 squared equals r squared. So we're going to solve for r. So we've got 64 plus 81 is equal to r squared. So we're simply going to say r is equal to the square root of 145. So I added these two together and then took the square root. So put that into here. So square root of 145. Okay, we are going to simplify this, and we're going to solve for dx dt. So notice that you can definitely divide both sides by 2. And then we're going to take and also divide both sides by 8. So here and here. Let's scroll up just a second here. And so we're going to clean this up and then solve for dx dt. So dx dt is equal to negative 1.5. That's a decimal point. Square root of 145, all being divided by 8. It doesn't really make a lot of sense, like in that form. That's the exact form. It's not really written correctly because we have a decimal as a part of a fraction. But if you go to your calculator and do this out, just make sure that you remember to close parentheses for what's underneath the radical before you divide it by 8. We should also include the whole numerator in parentheses as well. And this should work out to be approximately negative 2.26 feet per second. Okay, so the boat is moving towards the dock at a rate of 2.26 feet per second. And why is it negative? Well, it's negative because of the direction it's going. The distance between the dock and the boat is decreasing, so that's why dx dt is negative. Okay, in question 3 it says a rocket launch is being filmed from ground level at a distance of 3,000 feet from the launch pad. So that's this distance right here. This is where a camera is, and this is the angle of elevation theta. So that's going to change over time. And I know this rocket is really bad, but that's the best I can do with what I have for a stylus here. Okay, so this right here is going to be changing while the camera is filming the rocket. Again, this is the only number, the 3,000 feet stays stationary because our camera is over here at this point. Okay, it says the rocket is rising at a rate of 880 feet per second when it is 4,000 feet up. So the change in the height, or dh dt, is equal to 880 feet per second when h equals 4,000 feet. Well, when h equals 4,000 feet and this distance is 3,000 feet, you can find the hypotenuse of this right triangle. It would be 5,000 feet. This is just a multiple of a 3, 4, 5 right triangle. Okay, so it says how fast must the camera angle of elevation change at that instant to keep the rocket in sight? So we're being asked in this particular case to find d theta dt, which is something a little different. So change in theta with respect to time. So that means that we're going to have to use trig. So in here, we are going to want to work with a tangent function. So we're going to say tangent of theta is equal to the opposite side, which is the height, divided by the adjacent side, which is 3,000 feet. Okay, so here's why we want to use tangent, because it gives us 4,000 feet, which is changing, so that's why we put height in there. That's changing. That's going to give us dh dt, which we know, so we're going to be plugging that in there. The 3,000 is fixed. Okay, so that's a constant. And we're going to be looking for d theta dt. So that's going to come when we take the derivative here. Okay, so we are ready to take the derivative on both sides. So dt. So the derivative of tangent theta is going to give us secant squared theta d theta dt. And it looks like two d's there, so I try to write that again. Okay, so derivative of tangent. Can't talk and write at the same time, sorry. Derivative of tangent is what gives us secant squared theta, and they're going to have d theta dt. On the right hand side, don't use the quotient rule because treat it as 1 over 3,000, a constant, times the derivative of the height. So derivative of h would just be dh dt. Okay. All right, let's plug in what we know. Okay, well, we're running into a little bit of a problem right here because we have secant squared theta. We have to figure out the secant. So let's do a little bit of trig over here. Remember that secant of our angle theta would be equivalent to 1 divided by cosine. All right, cosine we can figure out is adjacent over hypotenuse. So that's why I really wanted to put that 5,000 in there. Is so that we can actually calculate the secant. So we have 1 divided by cosine, and our cosine is 3,000 divided by 5,000. So it's just going to give us the reciprocal. So really our secant is equal to 5,000 divided by 3,000, or simply 5/3. Okay, so come over here. Secant squared theta, we want to put in 5/3 for the secant. We have to square it. And then we're going to have d theta dt. That's equal to 1 over 3,000 times dh dt. Hey, we know that from up here. dh dt is 880. So go ahead and put it over 1. Let's scoot this up a little bit. Okay, so we're going to have 25 over 9 is equal to d, not equal to, sorry. 25 over 9 d theta dt is equal to 880 over 3,000. Okay, divide both sides by that 25 over 9. Or you could say multiply by the reciprocal. So I have 880 over 3,000. Sorry, I left off a 0 on that earlier step. They're going to multiply by the reciprocal, which is 9 over 25. And scoot it up one last time. Okay, and d theta dt, when all is said and done, after you go to the calculator and you multiply this out or simplify it, it's going to be equal to 0.1056, and that's in radians per second. Okay, and our last problem for today, this type of problem we'll call a cone problem, and this is what you're going to practice on your homework tonight. So suppose liquid is pouring through a cone-shaped filter that has a radius of 4 inches and a height of 16 inches. If the liquid is flowing out at 2 cubic inches per minute, how fast is the depth of the liquid changing when the level is 8 inches deep? Okay, so the volume of a cone, first of all, is equal to the formula 1/3 pi r squared h. So it's the area of the base, pi r squared, times the height, h, and then you take 1/3 of it. Okay, so in the given information, we are told that the radius is 4 inches when the height is 16 inches. We'll come back to that in a second. And then we're also told the change in the volume with respect to time is -2 cubic inches per minute. And we're asked to find dh dt, actually, when the depth is equal to, or the height, we should say, height is equal to 8. Okay, so you notice something in here. We have volume, we have radius, and we have height. Now, if we went and tried to take the derivative of both sides with respect to time in here, we'd run into a little bit of trouble. Okay, I fixed that. Because on the right-hand side, you notice that we have r squared and we have height. And so we'd really have to get into the product rule. But notice that our given information, we never talk about dr dt, or we don't talk about the radius beyond knowing that it's equal to 4 inches. So what makes the cone problem a little bit tricky is that we have to rewrite this equation in terms of just the height. So in other words, we have to figure out the connection between the radius and the height, or the ratio of the radius to the height. So if you take a look at that given information down here in this box, it says that r is equal to 4 inches when h is equal to 16 inches. So you could say that 4 times the radius is equal to the height. Okay, but we really want to take r out of that equation and replace it with h. So we're going to take and divide both sides by 4 and say that the radius of this cone is equal to the height divided by 4. So we have the radius written in terms of height. Okay, so before we take the derivative, let's take a second and rewrite this equation. V equals 1/3 pi. Okay, instead of r squared, we're going to take and put in h over 4. We're going to square that, and we're going to multiply by the height. Okay, so volume is equal to 1/3 pi times h squared over 16 times h. All I did was I squared what was in the parentheses. And then we're going to simplify this a little bit more, kind of clean it up, multiply those fractions together, multiply the h's together. And we're going to write this as 1 over 48, because that's 1/3 times 1/16 times pi times h to the third. It'll be a little bit easier if we don't write the h to the third in the numerator, because now we're getting ready to take the derivative, finally. Okay, so if we go ahead and take the derivative with respect to time, we're going to have dv dt is equal to 3, because that's that exponent, it's going to have to come out in front according to the power rule. 3 times 1 over 48 times pi. Remember, both the 1 over 48 and the pi are just numbers, they're constants. We have to subtract 1 from that exponent on h, so it's 3 times 1 over 48 times pi times h squared. And don't forget we have to put dh dt on the end. All right, let's plug in what we know. If we scroll back up here, we know that dv dt is equal to -2. So we're going to plug in -2 on the left-hand side. You can go ahead and clean this up if you wanted to. 3 times 1 over 48 is going to give us 1 over 16 times pi. Remember that our height was given to us as 8. That's at this particular moment in time we want height to be equal to 8. We're going to square that. And remember, the whole idea is we're solving for dh dt. Okay, so let's simplify. Over here, 8 squared gives us 64 over 16 times pi dh dt. We're almost done. And 64 over 16 simplifies to 4. Pi dh dt. Really, that was supposed to be a t up there. And then take and divide both sides by 4 pi. So we have -2 divided by 4 pi on the left, and that's equal to dh dt. Again, you can simplify it. So dh dt, the change in the height with respect to time, would be equal to -1 over 2 pi. But we probably would want to write this definitely in terms of the units. That's in inches per minute. So the cone, the level of liquid in the cone, is being reduced at a rate of 1 divided by 2 pi inches per minute. And that doesn't really make a whole lot of sense to us, but the decimal equivalent might. When you divide that out, you should get -0.1592 inches per minute. So the height of the liquid in this cone is going down by a rate of 0.1592 inches every minute. Okay, good luck with the homework problems. As always, I'll be answering some questions in class the next time I see you.